All right, guys, so we're going to start with another video today. We're actually starting topic 6, which is transverse shear. And some objectives for this topic are to determine shear stress in a beam that has a prismatic cross-section. So we're going to kind of be sticking to a very specific kind of cross-section, and material that is homogeneous and that stays in that kind of linear elastic zone. And we're also going to talk a little bit about shear flow. So there are some very specific objectives here that I want to kind of cover. And this is a kind of a big topic. It has a lot of different parts to it, but we're going to kind of just stick with these two, okay? We might be able to do this in one video. It's not that long, but we'll see. We might split it up into two. So we'll kind of just see how it goes. Okay. So to start with, we're talking about shear in straight members. So we know that beams mainly support moment, but they also support shear, okay? We've kind of already seen that when we have a beam, which is something that is transversely loaded like this, right? Let's say we have a simply supported beam. This kind of deflection from bending is what dominates this type of member. But we do also, in several cases, have to deal with shear. And we kind of have talked about this and always said like, oh, like ignore shear for now, let's not deal with it. Well, now we're going to kind of deal with that. So shear is the result of transverse shear stress distribution that acts over the beam's cross-section. So we already actually know this. This is just a cut. So here, this picture shows a long, that's not a straight line, sorry, shows a long member. Let's say it goes all in this direction. This is the length of the member in this direction. And we make a cut here. We know that when we make a cut, so let's say this was a member, we made a cut. This cut, we'd have shear that looks like this. It acts over the beam's cross-section. This would be our shear. And this is exactly what this shows. And we also know that shear, we talked about this way early on in like topic 2, shear has this special property called the complementary property of shear. And this shear force V creates corresponding longitudinal shear stresses, these taus, which act along the longitudinal planes of the beam. So if we kind of isolate this tiny element here, I'm going to zoom in right here, we have shear stress tau that acts in all these faces of the cross-section in these equal and opposite directions. Okay, so there's some important things we have to recall from previous classes, like statics, and from previous topics, like topic 2 from this this class. So now when we're talking about shear stress, a really good way to kind of understand what's happening here is if we consider the following 2 examples of a beam. So if we were to apply transverse loading, like this load P, to beams that are not, or boards that are not bonded together versus boards that are bonded together, we're going to have some very different things happen to these two. So I'll kind of show you, let me show you it in this picture here. Let me kind of draw this. So if we basically have all these boards, and the boards aren't glued together, and we zoom in on the end here. Let's say we zoom in on this end. What we're going to see is, we'll see this kind of, this is very exaggerated, but we'll see this kind of bending happening where everything kind of pulls out. So we'll see this jagged edge. And this is if we have some load P, okay? Whereas if these are bonded together, so that would be like this picture here. You kind of see this jagged edge happening here, okay? And if we have here, if we have this section here, this bonded beam, or all these boards are bonded together with some kind of glue or nails or whatever it may be, then we're transferring shear. So shear is being transferred. And this here, this shear that's being transferred, this keeps things together. Okay. And this is basically, this is the behavior of a beam. This kind of defines this right here. This defines beam behavior. That everything works cohesively. This here, this is not a beam. Not beam behavior. We don't really have things that just work on their own accord like this. So for this class, and by the way, just as a side note here, we cannot use this formula. We cannot use MC over I here. We can't use it because this doesn't act as a beam. It's not linear. It's not a continuous edge, and it doesn't follow beam behavior. So here, this is what we're going to assume for this class, that all of these boards stay bonded together. This is the assumption we'll kind of use for this class. Okay. So here, this image shows you basically distortion of a beam due to shear. So how does a beam distort when we apply this kind of transverse, this shear loading, when we have a cut here? What happens when we applied that kind of force? And this is what it would look like after deformation. So we want to kind of consider this as a highly deformable body so that we can understand what these look like. And I'll kind of let you guys read through this slide. But right now what we're going to do is we're going to take some time to derive the shear formula, okay? So here, let's start, let me get everything set up here. And this is the shear flow formula. Okay, so this is not the same thing as tau is equal to V over A. This is the shear flow formula. So we're going to start by considering some beam. And we're going to say that this is a simply supported beam, like this. And then we're going to apply some distributed loading to this beam. It's not necessarily constant, but just some distributed loading here. Okay. And we'll say that this cross-section, the cross-section of this element, is some awkward shape. It's not necessarily a shape that we know. Okay. And we'll say that this is the geometric centroid. So let's say this is our cross-section, just so we can kind of generalize what's happening here. And then we'll say that this is our geometric centroid. All right. And let's say we take a cut. Okay, let's make a cut. We like making cuts, these little differential elements, so that we can kind of understand what's happening. So this is our cut dx, okay? And then we're going to zoom in on this cut. And this is what that looks like, basically. I'm going to take that cut just like it is. This would be the dx. So this is not the cross section. This is just this tiny element here that I'm getting. This is all of this here. Okay. And what I see here when I make this cut is I've exposed some shear, right? So we'll say on this side I've exposed some V, but on this side I would have V plus some change in V, or on the other side of the cut. And then I'd also have a moment on this side. And then on this side, I'd have some moment plus some change in moment, because I have some distance that I've applied this to, okay? So this internal moment and shear, they're changing as a function of x. So they're changing as a function of x, right? So let's come here and let's draw this stress profile. Let's draw the stress profile so we can understand what's happening and how we can further analyze this system. So if this is the same, I'm just kind of blowing this up a little bit. This is still dx here. I'm just blowing this all up so we can see what happens. And let's say that our neutral axis is located somewhere here, some arbitrary location that we don't necessarily know yet. Okay? And what's happening here is my bottom, actually let me pick a different color here. My bottom is experiencing this tension and then the top is experiencing some compression right? This is my sigma. This is sigma prime because I have some different moment. Okay, this would be where my M is applied. This is my M plus some change in moment, right? And then I want to look at just now some location above the neutral axis, any location, so I can derive it for any place on this beam, Y, okay? So I'm going to come here and I'm going to say, let me cut right here and let me zoom in. Let's do an FBD of the cut. And what do I have? I'm going to cut this right here, make a little cut there. So I'm just going to draw the top portion of that. I have a cut. And I still have now some value of sigma like this. It's like a trapezoid now. And this is sigma prime. Sigma is not equal to sigma prime because we have different moments. Okay, just so we remember. And then here, since we're taking this cut, let's sum forces in the x direction and set them equal to 0. We have the integral of sigma times dA1 minus the integral of sigma sigma prime. And what is dA1? dA1 is this cross-sectional area here. So this is dA1, this is dA1, right? And then plus tau times dx times b. This is the width. The width is b. Okay, and this all has to equal 0 because we have to meet equilibrium. All right, so what happens is let's plug in what we know. Let's plug in our formula mc over I or my over I because it's at some y value. It's not necessarily at c right now. So what we'd have here is sigma of integral of my over I dA1 minus the integral of m plus dm y over I dA1 plus tau dx times b equals 0. Okay, and then we have basically tau dx times b, that width is equal to, because these m's you can see, this m cancels out with this part here, and we're just left with dm over I y dA1. And we know I is constant here, so I is constant, we can take it out, and we get tau is equal to dm over dx, if we kind of simplify all this, 1 over IB integral of y dA1. And here we know some things. We know that dm over dx, the change of moment with respect to with respect to x, this is just the shear. Right? The derivative of moment is just shear. So we can further simplify this and say, well then tau is just equal to v over IB integral of y dA1. And this here is the first moment of area, and it's basically the moment of area about the NA. It's the moment of area about the neutral axis, and we give this a symbol Q. We call it Q. Okay, and here let me write out what this is now. Our final formula, tau is equal to VQ over IB, and this is our shear stress formula. So now this gives us the shear stress due to basically at some location in the beam. Here, let me write it here for you. So this is our shear stress formula. But if we wanted it at any location, tau equals VQ over IT, and T would be the width at location you want the stress at, because remember, B is the entire width. So these are two very important formulas. Okay, so now this was kind of a generalized formula, but now let's look at shear stress in a rectangular beam. Okay, so here, right, shear stress in a rectangular Okay, so what happens is, let me draw out what this cross section would look like. So now this would be my cross section. This is that width, okay? My neutral axis would be right here in the middle. this whole thing would be h, so this would be h over 2 and h over 2. And then here at this point, at some location, we would call this, let's say, y1, right? What I would need to do is basically find that first moment of area. So if I have this equation, VQ over IB, let's say T is equal to B, and I is equal to the moment of inertia. And we know for a rectangular section, that's just 1 over 12 BH cubed. So we have all that. Okay. And then here, Q, this is the new stuff. Q is equal to the first moment area, right? We know that, about the NA, which is equal to the sum of the area, and I'll show you which area we're talking about, times the Y bar, which is very similar to that YA that we've already done in topic, or I think it was the last topic, topic 5, but I'll do it here again. So what A1 is all area above where you want to calculate shear stress, and Y1 bar is equal to the centroid of A1 measured from the NA. And I'll show you exactly what that means. So let's take a look at this section right here. Let's say this was that Y1 that I'm interested in. So this whole section here, I would need to get the area of this section. This would be my A1. If that's my A1, then my Y bar, my Y1 bar, would be the geometric centroid of this area measured to the neutral axis here. Okay, and how do we get that? It would basically be, you can see here, I put in a different color. It would be this Y1 plus H over 2 over 2, half of it, okay? And we'll do a couple more of those so we can see how that's kind of further done in some other applications. Okay, so now let me show you where this cut came from in case this was a little bit confusing. So let me try to draw this out. So here, actually let me start with drawing the whole, let's see how I can draw this in 3D and make it look right. Okay, it's not terrible. Let me try that again. Okay, you can kind of see what I'm talking about. So basically what this is a cut here. This here is a cut. So we already have a picture of it. And this is the shear. What's happening is the shear is small, it gets bigger towards the center, bigger, and then becomes small again. So you have small, bigger, small, smallest, small, bigger, these are all bigger, small, small. You see. So the center where the neutral axis is, that's the biggest. And we kind of just put this whole V, I'm gonna try to, this whole resultant V here, but really it's all these small little values of V. And this would be our neutral axis. That's so bad. Let me try this again. That's better. Okay. This is our NA. This green line. Okay. And our shear stress distribution here it's actually parabolic. That's why it's small, bigger, bigger, small again. Okay. And it's the max in the middle at the neutral axis. Okay, and this is basically this picture. This is our shear stress profile. Okay, and I can draw this a little bit better for you with like the stick figure diagrams, not the 3D maybe, if we kind of look at something that looks like this here. This is the profile, and the distribution here is actually a parabola. just don't like this. Okay, let's see. Kind of better. Okay. And this is that distribution. So small, small, bigger, small, smallest. And this here, this is our max at the neutral axis. What happened to my profile? Hold on. There we go. This is our NA. Okay, and now what we want to do, so this was the cross section here of this figure. And now what we want to do, let's plug everything into our shear formula, that shear flow formula. Okay, so let's plug everything into our shear flow formula. Tau equals VQ over IB. And we get VB times H over 2 minus Y1 plus 1/2 times H over 2 minus Y1 over 1 over 12 BH cubed times B. Let me actually show you where we got the full Q value from here. The full Q value here. So once we get all of those heights, we get Q is equal to B times H over 2 minus Y1. So H over 2 minus Y1, that gives us this. And then times B, so this is the area. So B times H over 2 minus Y1, this is the area, okay? And then times Y1 bar, right? And how do we get Y1 bar? Y1 bar is equal to Y1 plus 1/2 of H over 2 minus Y1, because Y1 bar is the distance from this point to the neutral axis here. That's what we had already solved for. That's basically what we came and plugged in here for Q. Okay, once we plug everything in, let's continue. We end up getting 12V over BH cubed, H squared over 8 minus Y1 squared over 2. And then we can solve further and we get 6V over BH cubed times H squared over 4 minus Y1 squared. And we can see this is a parabola. It makes sense. This is parabolic. All right? Y1 varies parabolically. It's a second order function, okay? And we can notice some special things here. So when Y1 is equal to H over 2, this is either at the top or the bottom, we have H squared over 4 minus Y1 squared equals 0, and we get tau equals 0. And we can also see that when Y1 equals 0, this is when tau is max. And this is at the neutral axis, basically, so when it coincides. Another way of doing this, if you didn't know, you can take the derivative. You can say d tau over dy1 equals 0, and we can solve for y1, and we'll get that place when it'll equal 0. So we'll do it in a couple of different ways. But let's look first at some limitations of the shear formula. I know this is a really text-heavy slide, so I won't go over too much of it. I'll let you guys read it for the most part. But there is one thing that's really important. A major assumption when we develop the shear formula is that shear stress is uniformly distributed over the width T at the section. Okay, so this assumption means that the average shear stress is calculated across the width. Now this is kind of true for lesser values of the B over H ratio, but as we increase that ratio of B to H, this formula becomes less and less accurate. So what we need to do basically is we need to take some special considerations when we have these junctions. So a flange web junction is something like this, where the flange and web meet. And I'll kind of show you what our shear stress profile will look like when we have that junction. But the good thing is that these limitations aren't a huge problem for engineering practice, because most of the time we're only interested in calculating the max shear stress in a beam, which really occurs at the neutral axis here. So this point here isn't such a big point of interest for us. Like, it's fine if we aren't getting accurate values there, because we really just want that maximum shear stress so we can design for maximum conditions. Okay. But I will show you how we can kind of fix that. Okay, so a summary of the shear formula. These are some pictures from the book that are a lot prettier than the ones I could draw, so I put them here for you. This is our profile. This is everything you need to know about that shear formula, the shear flow formula, and how you can calculate it. Okay, and we're gonna go through our first example now. Okay, so I'm gonna draw this beam. And let's give this a W value equal to 200 pounds per foot. And this, we'll call this point A, point B. So here you can, this length is 8 feet. This would be 1,600 pounds. And so this is symmetric. We would get 800 pounds, 800 pounds. Okay. And what we want to do, we want to find the max shear stress. So let me write that in the problem statement. Alrighty, so what we need to do here is let's make a cut somewhere. Let's make a cut somewhere. So let's make our little cut right here. Okay, and actually I'm going to show you what the cross section looks like here, because we would need the cross section of this element. So the cross section here, this is an I-beam or a wide flange. This would all be given in the problem statement, actually. So the cross section has to be given here too. And then this width is also 2 inches. And then our neutral axis is in the middle. It's all symmetric, so we're all good. Okay, so this is what you'd be given. And basically the solution starts from here. So the first step is to draw the shear diagram. Okay, so pretty simple for this. We're going up 800, straight line because we have a constant distributed load. And then we get pushed back up to 800 here. So this is 800. This would be negative 800. And this is our shear diagram. And since everything here is nice, symmetric, and easy, this is 4 feet. Okay. So we see some interesting takeaways here that we kind of already knew, right? We see that our max V is at the supports. That's the first thing that we needed to figure out. Okay, the next thing that we need is that our max tau, we know this, for the cross section, is at the neutral axis. And this is always for linear elastic material. So these are the two really important points. So two important items we need to know or use to calculate tau. Okay, so now that we know those two really important things, we can continue. And let's now talk about the geometric properties that we need. So geometric properties. So we need these three things. We need I, we need T, and we need Q. So let's start doing these one at a time. Let's first find the moment of inertia. So moment of inertia here, we have an I-beam. You can either do this using parallel axis theorem. We'll do it the block way this time. I think we did parallel axis theorem last time. You can do either of these. I'm going to take the moment of inertia of the whole thing, and then I'm going to cut out the moment of inertia of the holes. So basically, I get I about the NA is equal to, let me put in some, actually I should have probably just copied this. So we have all the values. Okay, there we go. So I is going to be 1 over 12, B, which is 8, H, which is 12, 8 plus 2 plus 2, cubed. That's for the entire thing, as if this was just one rectangle. But now I need to subtract the holes. I have 2 holes. Let me draw those in here. These are the holes that we're subtracting. Okay. Minus 2 times 1 over 12 times 3 times 8 cubed. The 8 is the height, the 3 is the width from here to here. And we get 896 inches to the 4th. So just so we all know, this is I for the holes. All right, okay. Now for the fun stuff, let's calculate Q. Okay, the T is what? The T is easy actually. Let's do the T first. The T is just 2 inches, right? The T is just the width where the neutral axis is. That will be right here, and we know the width is 2 inches. So that part is done. The I is done. Let's highlight these so we know we're done with them. Okay, the next thing, this is the fun part. So now let's do Q. But to do Q, I'm also going to come grab this picture again because we're going to use this and kind of blow it up. Make it a little bigger here. Even put it on this part. Okay. So what we need to do here, we know that Q is equal to the sum of the areas times y bar prime for each area. Okay, so here what we want to do is we want to look at all of the areas either below or above the neutral axis. You can pick either one and you'll get the same answer. So because this is symmetric to it really doesn't matter what we look at. Let's do all the area above. So the areas that we have above the neutral axis, I'm going to split them up into rectangles so I don't have to deal with complicated moment of inertia shapes. So this is going to be my first area. I'm going to call this area 1. And then the second area that I'm going to deal with, I'll do this one in purple, is going to be this area here. This is all the area above the neutral axis, and I'm going to call this area 2. Okay, so what I need first is to get the area. So let's do the area. This is the easy part. So let's do area of section 1 is going to be half of 8, which is 4, times the thickness, which is 2, and that's 8. Now, the area of section 2 is going to be 8 times 2, which is 16. Okay, not so bad. So the fun stuff comes when we're trying to calculate the y bars for each of these areas. So here is, what color have I not used? Let's try green. So here is the location of the neutral axis. And then you want to find the geometric centroid of the small area that you're dealing with and calculate the distance from the geometric centroid of that area to the neutral axis. So here, the distance, if this whole part is 4 inches, this is 2 inches. So I'll put this in blue, my y prime 1, we called this bar, is equal to 2 inches. This is inches squared. Okay. Now for the second part, here is the geometric centroid of that second part right in the middle. And the distance from this geometric centroid to the neutral axis, all I have to do, this to this is 4 inches, right? Here to here is 1 inch, so the total is 5 inches. So my y2 bar is equal to 5 inches. And now all I have to do is sum everything up. So Q is equal to 8 inches squared times 2 inches plus 16 inches squared times 5 inches. And I get 96 inches cubed. Okay, so if you just keep it really organized like this, then you'll get the right answer and it'll all be good. Okay, now we can plug everything in and we get tau max is equal to 800 pounds times 96 inches cubed divided by 896 inches to the fourth times 2 inches, and we get tau max equals 42.86 psi. Okay, so not too bad. Let's try another example now. Okay. So the beam shown in this figure is made from 2 boards. Determine the maximum shear stress in the glue necessary to hold the boards together along the seam where they're joined. Okay, so what we'll probably do, we'll probably finish this example and then I'll post the next half of this in another video because it's getting a little bit long. Okay, so here, let's take a look at what's happening. We have a distributed load of 6.5, which means our resultant here is 26. And I'll let you guys do the statics on your own, but we get 6.5 kilonewtons and we get 19.5 kilonewtons here. And they're giving us this cross section, it's a T shape. Okay, so if we want to draw the shear diagram corresponding to this loading, we would get something, try it from here, constant shear up until this point, and then we have some linear function here. So this would be shear in Kn, this is 6.5, and this is negative 19.5. Okay, so now let's take a look at what we need here. So we have this T shape, and our centroid is going to be determined from the reference axis, which we'll use as the bottom. So we're going to use the bottom of this here as our reference axis, and they kind of show us that in this picture that they're, I think I drew on it, let me take this out. They're calculating Y bar from this point. So we're going to use the point they're telling us as our reference axis. Okay, so what that means is here, we're going to say that our Y bar is equal. We need to figure out where the neutral axis is because this is not a symmetric shape. To find it, we say Y bar, the location of the neutral axis, is equal to all of the Y's times the area divided by the areas. Okay, so let's just follow this picture. And let's come here. So the first thing we want to do is let's calculate all of these values above. So we get this 0.075 times 0.15. That's going to be the half of this 150, okay? And then times 0.03, which is that 30 millimeters. And then plus 0.165 times 0.03 times 0.15, and that's going to be divided by just the area, so just the 0.15 times 0.03. This is of the top of the T shape, plus then the 0.03 times 0.15, the bottom of the T shape, and we get 0.120 meters, which means that this location here is 0.120 meters. And it makes sense because that is in line with like below this 150, which we know it has to be somewhere there, but closer to the top because that's where most of the area occurs at. Okay, now that we've calculated the location of the neutral axis, we can calculate our moment of inertia. So we know that I, our moment of inertia, is going to be 1 over 12 times b, which is 0.03, times h cubed, and then plus, we're doing parallel axis theorem, times 0.3 times 0.12 minus 0.075 squared. So we've done this a couple of times now, so you guys should be able to calculate these on your own. So make sure you're getting these values when you're trying this. Oops. And we get a value here of 27 times 10 to the negative 6 meters to the fourth. Okay, so the top flange here is being held on the bottom board by the glue. So the glue is right here, where I put the blue mark, okay? And it's applied over this thickness of 0.03 meters, this 30 millimeters. So it's applied right here in this thickness of 30 millimeters. Okay, and A prime is defined as the area of the top board. So what we want to do here is we're going to now calculate that Q value. So Q we know is equal to Y bar prime, A prime, and we get here. So I went through this pretty slowly in the other example, so make sure you can get these numbers on your own now. And we get a total value of 25 times 10 to the negative 3 meters cubed. And now we can plug into our shear flow equation. And we get 4.88 MPa. And basically, this is our resistance to the longitudinal shear stress that holds the boards from slipping at the right-hand support. So this is our answer here. Okay, and we're using that 19.5. So if we're going to draw this out, let me see if I can draw this. This is our, what we're saying is that this shear, this 19.5 kilonewton, and this would be this here is the plane containing the glue. And this is that 4.88 megapascals. Okay, so we'll stop here with this video and we'll continue next time with example 3 and some more information about shear.